before we conclude these introductory remarks, I want to give you a little bit of an idea of how some of these ideal scenarios will come into real life. And I have actually chosen an example here that we can discuss, which is related specifically to digital circuits, mostly because a lot of you can actually understand how transmission lines impact RF circuits. But the reality is that after we basically got into the gigahertz era of microprocessors, nowadays transmission line theory is actually required to design a digital chip or a microprocessor. So this is an image I took from the IBM website that actually shows copper interconnects that you will find out in a typical microprocessor today. We'll discuss the copper in just a little bit, but first of all, let me just give you an idea of how important this thing is. So on a typical large-scale VLSI circuit, which might be just as large as your thumbnail, you will find out about 30 miles of interconnects. So if you think that this interconnect is a small deal, it's actually a big deal. Again, in a thumbnail of circuit, you will have about 30 miles of copper. So we're talking about a ton of interconnects, a ton of distances that actually signals have to propagate through. And those interconnects have to connect billions of transistors in that type of a chip. And those are basically multi-layer. In a modern VLSI circuit, you will actually have between 13 to 15 layers of those type of interconnects. So it's not like a single street highway. And actually, it's those interconnects that will slow down your circuit. In other words, if you think of an analogy, you can buy the best sports cars in the world that you like. But if you have no road to drive it, you can't go very fast. It's the same thing here. You can have an incredibly fast transistor, but if you can't send electrons fast enough from one point to the other, basically you don't have a fast microprocessor. So that's why this thing is really, really hard. It's really, really important. Now, as you may know, for many, many decades, actually, we had aluminum interconnects that were the case basically up to about 20 years ago. But 20 years ago, there was a revolution, and specifically in 1997, for the first time in industry, we were able to have copper interconnects, and that picture actually shows that. Now, you may wonder, why did we do that? Well, there are lots of reasons. Copper is actually less lossy than aluminum. It's basically simply more conductive. In fact, it's about 40% more conductive than aluminum, which, again, it translates into both loss as well as speed. In fact, with copper, you can actually improve the speed by about 15%. Just because the RC product, which is related to the delay in a digital circuit, is basically smaller in copper than it is in aluminum. So when actually IBM launched that, not only they were able to get better circuits, but they were able to, of course, to get faster speeds out of these interconnects. But copper is not just better from a performance point of view. It's actually much more reliable and much more durable. In other words, those lines tend to fail much, much slower than aluminum. So when that actually rocked the industry back about 20 years ago, basically that led to huge advantages of improving integration, improving memory, improving multi-core processors, and essentially it had a wave effect throughout the whole industry. Now, of course, the natural question is, if copper is so much good, so much better actually than aluminum, why were we using aluminum in the first place? Did we get this wrong? The answer is no, we didn't get that wrong, but copper is actually much harder to make it work. The reason for that is because copper atoms have this annoying property of diffusing through barriers in the processor. So even if you put this copper line, if you do nothing, eventually those copper will actually sink through silicon and will actually change its properties. So it took actually a lot of investment for this manufacturing process to actually make work. And nowadays, of course, we have it, but it took a lot of man hours and a lot of billions of dollars to basically make this thing work. So again, the reason I want to show you this example is because understanding transmission line theory is hugely important, both for analog as well as digital circuits. And people have spent tremendous amount of time making things work well, even in a relatively minor or what might appear minor change from aluminum to copper.